Okay, let's continue with, in this case, matrix multiplication, which is quite different from the scalar multiplication that we saw earlier. Scalar multiplication dealt with multiplying a matrix by a constant. Matrix multiplication is completely different when you're multiplying a matrix times another matrix. So important thing is to know how it's defined. So matrix multiplication is defined as a row by column operation. That means if we want to multiply two matrices A and B, we'd multiply the elements in a row of A by the elements in a column of B and then add the results. It's awkward and it takes a while to get used to this process of multiplication. So I'll take this first example just to kind of help you think about the process, to get your brain wrapped around the row by column operation. First, let's look at the dimensions of our matrix. This first matrix is a 2 by 3 matrix, the size of it. Our second matrix is a 3 row by 2 column matrix. Now, since this is a row by column operation, I've got to watch my dimensions and see if they'll work when I multiply a row by a column. Row of the first by a column of the second. So I'm going to take a row of my matrix, first matrix, and multiply it by a column of my second matrix. The number of elements I have going across has to equal the number of elements that I have going down, which means this number has to match this number in our dimension in order for us to multiply. So the two inside numbers must match. And they do. 3 across, 3 down, I'm good to multiply. So this says multiply the elements in a row of A by the elements in a column of B. And once I do that, then I'm going to add the results. So let's see what gets multiplied. I'll have a 2 times a 1, the negative 1, a 6 times a 1, and a 0 times a 0. So 2 multiplies by negative 1, 6 by 1, 0 by 0. Entry for entry, across and down. So those three results, 2 times negative 1 is a negative 2, 6 times 1 is a 6, and 0 times 0 is a 0. So I get 3 products, 2 times negative 1, 6 times 1, 0 times 0, and then I take those 3 results and add them together. Negative 2 plus 6 plus 0 is 4. Notice how big I have my answer set up to be. It's set up as a 2 by 2, 2 rows by 2 columns. That size comes from these 2 numbers on the outside. The insides must match to multiply. The size of your answer is going to be the 2 outside dimensions here, 2 by 2. Failed to mention that. Okay, so we multiplied row 1 by column 1, and we put the answer in the 1, 1 position. First row, first column. Now I'm going to multiply the first row by the second column. Entry for entry, just like I did over here. So first row times the second column means I'm going to multiply the 2 times the 2, the 6 times the 4, the 0 times the negative 3. So 2 times 2 will be 4, 6 times 4 will be 24, and 0 times negative 3 will be 0. Then I take those 3 results and add them up. 4 plus 24 plus 0 is going to be 28. And notice where I put that answer. I put it in the first row, second column position. 1, 2. Now I'm done with the first row because I've multiplied it by the first 2 columns. So now let's jump to the second row. So I am now going to take row 2 and multiply it by column 1, then column 2. So row 1 by column 1 will look like this, and what's going to get multiplied will be 0 times -1, -4 times 1, and then 5 times 0, across, down. The three products are 0 times -1, which is 0, -4 times 1, which is -4, and 5 times 0, which is 0. Three products, add the results, we get -4, and notice where we put it. We multiplied row 2 by column 1, so we put it in the row 2, column 1 position. Let's do that with our last row and our last column. I think that was a 0. Last row by the last column. Entry for entry, then add the results. 0 times 2, -4 times 4, 5 times -3. So 0 times 2 is 0, -4 times 4 is a -16, and 5 times -3 is a -15. Adding those three results gives me a -31, and notice I placed that in the second row, second column position. That's how matrix multiplication works, not what you would expect. But make sure you understand the definition, and remember, it's a row by column operation. Row of the first times the column of the second. So the answer we're looking for, all this stuff is extra. We're looking for the matrix with those four values, those four red values in those positions. What I've done on the top of the next page is just explain which entries get multiplied. Row 1 gets multiplied by, well, I should say row 1 by column 1, entry for entry, add the results, place the answer in the 1, 1 position. Row 1 by column 2, entry for entry, add the results, put it in the 1, 2 position. We'll do some more of this. Let's just check out the dimensions. I mentioned that on the other page, but let's see what has to happen in order for us to multiply. In order for us to multiply two matrices, we don't have to have the fact that they have to be the same size, like when we added or subtracted. Here, the dimensions have to be this. The number of columns in the first matrix must match the number of rows in the second matrix. And what that means is this inside dimension must match that dimension. The two inside numbers must match, and the result will always be the size of the remaining two values, m by p. So that's going to be our result. So I've given some scenarios where I have some matrix sizes, some dimensions, and I want to know if it's possible to multiply them, and if it is, what would the size of the resulting matrix be? So is it possible to multiply a 4 by 4 times a 4 by 3? First check to see if the inside numbers are equal, and if they are, then yes, it's possible. How big will the answer be? It will always be the two outside dimensions. So the answer will be 4 by 3. Let's look at the next one. 2 by 2 times a 2 by 1. Is it possible? Inside numbers match, so yes. How big is the answer going to be? The two outside dimensions, which will be 2 by 1. Is it possible to multiply a 4 by 3 by a 4 by 3? They're the same size. I could add them, but I can't multiply them because the inside numbers don't match. What about a 5 by 1, 1 by 5? Insides match, so it's possible. How big will the result be? Oops, 5 by 5. And finally, I can multiply a 4 by 4 because the insides match. 4 by 4 times a 4 by 4, and the result is going to be the size of a 4 by 4. That must take place before you can do the actual multiplication, so I suggest that you always check the dimensions first. So let's do some more multiplication. I want to multiply A times G. Well, let's go back to the previous page, find A and G. Okay, there's A and G. I want to multiply these two matrices, and based on the definition, let's check out the dimensions. A 2 by 2 times a 2 by 2. Yep, that's possible. Now, let's go ahead and do the row by column operation. So, a row of A times a column of B, then add the results. So 2, 6 times 3, 0 will be 2 times 3, which is 6. 6 times 0, which is 0. So I'll have 6 plus 0, which is 6. 2, 6 times our next column, 4, 7, will be 2 times 4 and 6 times 7. So 2 times 4 is 8. 6 times 7 is 42. So 42 plus 8 would be 50. Check my arithmetic. Is that right? I'll have to go back and check that. Okay, 4 times 2 is 8. 6 times 7 is 42, and 42 plus 8 is 50. Okay. Now let's jump to the second row. Times column 1, then column 2. So I get 0 times 3 and negative 4 times 0. Well, 0 times 3 is 0. Negative 4 times 0 is 0. So I end up with 0 plus 0, which is 0. And let's do row 2 by column 2. 0 times 4, negative 4 times 7. So 0 times 4 is 0. Negative 4 times 7 is a negative 28. So if I add a 0 to a negative 28, I'll get negative 28. But 50 is bothering me. Let me do that one again. 2 times 4 is 8. 6 times 7 is 42. So 8 plus 42 is 50. All right. Anyway, I'll show you how to do this on your calculator so you won't have any trouble with some careless arithmetic mistakes. Let's check out the next one. We want F times B. Okay, here's F times B. Pulled F and B from the second page, and let's multiply them. Looking at the sizes, check out the dimensions, because the dimensions have to work for us to, in order for us to do that. So I'm going to multiply row by column. The size of this matrix is a 3 by 3. This one is a 3 by 3. So yep, I can multiply it, and the answer is going to be as big as a 3 by 3. Kind of running out of room here, but I'll do the best I can to squeeze that in. So a row times a column. You're going to notice something interesting with this one as you start to multiply it. The way matrix B is set up, it's actually called an identity matrix. It should name the same identical matrix F. Let's see. Negative 1 times 1 is 1. Negative 1, sorry. 3 times 0 is 0. 6 times 0 is 0. So these two products will be 0, so I'm just left with negative 1 times 1, which is negative 1. Watch when I multiply it by the second column. Negative 1 times 0, 3 times 1, 6 times 0. So negative 1 times 0 is 0, 3 times 1 is 3, 6 times 0 is 0, so I'm just left with the number 3. Let's do first row times the third column. Negative 1 times 0 is 0, 3 times 0 is 0, 6 times 1 is 6. Notice I get a negative 1, 3, 6, which is the first row of matrix F. If I continue this, if I continue to multiply this, what was that number? That number was 3. Multiply second row by all 3 columns, third row by all 3 columns. It's going to end up naming the exact same matrix. Now, I would like you to go through it and finish it and show that, but I keep erasing my matrix, and so I want to do the least amount of writing on that as possible. Okay, let's look at G times D. I pulled G and D from the second page, and notice matrix D has some variables in it. So we've got to be careful with those, but we'll just have algebraic expressions instead of just constants like we see over here. And I can multiply them because this is a 2 by 2, this is a 2 by 3, insides match, so the answer will be as big as a 2 by 3 matrix. So let's go row, column. This row by this first column. 3 times 3, 9. 4 times 1 is 4. So 9 plus 4 will be 13. Now let's go first row times the second column. It'll be 3 times a half, then 4 times x. Well, 3 times a half, let me erase this one so we don't get that confused. 3 times the 1/2 will be 3 halves. 4 times x is 4x, so it'll be 3 halves plus 4x. It'll be an expression rather than a single value. And finally, let's do, to complete the first row, for row 1, which is 3, 4, times column 3, which is 5y. So 3 times 5 plus 4 times y. 3 times 5 is 15 plus 4y. Just keep it as that expression. That takes care of row 1 times all 3 columns. Now we have to do this again with row 2 times all 3 columns again. So 0, 0 times 3, then negative 7 times 1. Well, that first product is 0, the second one is negative 7, so we'll just end up with a negative 7. Now let's multiply it by second column. 0 times a half, negative 7 times x. Well, 0 times a half is just 0, so negative 7 times x is just negative 7x. Then finally, 0, negative 7 times our very last column, 5y. 0 times 5 is 0. Negative 7 times y is a negative 7y. So I have 0 minus 7y, which is a negative 7y.